Good morning. This is my best Morgan Freeman voice. I will not be delivering this lecture in my Morgan Freeman voice, but I did want to say good morning. So, I'm Dane Quinn from the University of Akron, and today I'd like to do an example with a multi-degree of freedom system, and this is for fundamentals of vibrations. So, let's look at the following system. We have a disk here of radius r, mass m, and it also has an inner hub with half the radius. So to that inner hub is connected a cable with a spring and then grounded. Then on the outer hub there's a second cable which is wrapped around, and that's connected to a spring that then supports a block of mass m. Each of these springs have identical spring constants, k, and I'd like to find the equations of motion for the system in terms of the rotation of the disk, right, so an angle that measures how this disk rotates, and the displacement of the block with respect to the ground. So when we do this, we start off and think about the problem a little bit, coordinates and directions, then we identify the kinematics, we define the free body diagram, finally we put it all together with the equations of motion. Right, so let's start off and think a little bit about the objects and the motion, as well as identify the forces. Right, so here we have the disk, right, and I'll draw the inner hub here. Right. Then we have the second object is the mass block. So now, these two objects, if I look at the system, it's a 2 degree of freedom system. Right? So this system has 2 degrees of freedom. So there are 2 independent coordinates that are required to define the configuration. So here, the best way to see that is to take one of these objects, say maybe the disk, and define a coordinate that determines its configuration, like the rotation of the disk. Then if I hold that coordinate fixed, can anything else move? Well, in this case, yes, the block can still move up and down because it's connected with a spring. So then if I take a second coordinate and identify the position of the block, then everything is fixed. I can find all the material points with those 2 coordinates. So again, it's a 2 degree of freedom system, which means ultimately we'll have 2 equations of motion. So now if I go back to this, the objects that we've drawn here, and identify the forces. Well, there's going to be a reaction force that acts at the center here. There's going to be a force due to the spring over on the right. Then there's going to be a second force acting on the disk due to this spring that suspends the block, which will then be balanced by this force acting on the block. So let's go and define those. The reaction force, we'll call it R. Right, so again, R is a reaction force. Let's define this spring force as Fs, comma 1. Right, so this is a spring force. And then this force we'll define as Fs2, because these are internal forces, both arising from the spring. They have to be of equal magnitude in opposite directions. So this force would be minus Fs2. So again, this is our second spring force. So now, just kind of thinking ahead, this disk rotates, right? So we'll need a coordinate that describes the rotation. This block moves up and down, so we will need a coordinate that describes its motion. And then if I look at these forces, the spring forces come from constitutive laws, so we'll have to also measure the stretch in each of these 2 springs. The reaction force is not derived from a constitutive law. Instead, we'll just have some unknown components. Okay, so let's go and do that. All right, so let's try to define these coordinates. So in particular, if I start off with the motion, we can define the angle theta for the rotation of the disk. Then for the position of the block, we can define that as x. So again, with these two coordinates, we can identify the configuration of the system. But again, going back thinking about these forces, these two forces will require different measurements, right? In particular, this force will require the stretch in the spring. So let's put a little dot there and look at how much this spring stretches, and we'll define that as y. Then we'll look at the stretch across this spring. Notice that as the disk rotates, this top point can move up and down, and then the block can move relative to that, right? So we'll actually need two coordinates here, right? One, say w, for the motion of the top point, and then z will describe the stretch in the actual spring. So now, again, it's a 2 degree of freedom system. So we need two coordinates. To define the configuration. Notice though that we've actually defined 5 coordinates, right? 1, 2, 3, 4, 5. So some of these coordinates are dependent on one another. So let's look. In fact, we need 3 relationships, right? Because we have 5 coordinates and only 2 of them are independent. Let's examine y and theta. These two are definitely related because as the disk rotates, this spring stretches, right? So looking at some simple kinematics, we can say that y is r over 2 times theta. Likewise, if I look at this point above the spring, as the disk rotates, this point, defined by w, moves up and down, right? So here w is r times theta. Notice that these are dependent coordinates, right? If I know one of them, I can find the other two. Then our final relationship is sort of described over here. And in particular, we see that x is equal to z plus w. So if I know x and I know w, I can find z. So we have these 3 coordinate relationships, which take our 5 coordinates down to 2 independent coordinates. So now if I think about the kinematics, how do we describe the motion? Well, looking at the disk, it rotates. So we can define the angular acceleration of the disk in terms of theta, right? And in particular, it's theta double dot in the k direction. The block translates up and down. So we can identify the acceleration of the block as minus x double dot in the j direction. Again, this negative sign comes from the way that we've defined x. So if x is positive, this block is displaced down. If x dot is positive, the block is moving down. So the velocity would be in the minus j direction, right? So I and j are given as so. Then if x double dot is greater than 0, then the block is clearly accelerating downward, and that's in the minus j direction. So we have to make sure that the signs and the way that we identify the kinematics is consistent with the way that we define the directions and the coordinates. Okay, so now let's turn to free body diagram. I went ahead and reproduced the coordinates that we defined previously, and so we'll use those to identify the forces. So again, we had a reaction force, we had F, S, 1. This we said was, let's put it over here, Fs2. And then this force is minus Fs2. So these are all spring forces, right? And they all have constitutive relationships. So in particular, if I look at Fs1, then if y is positive and this block is being pulled to the left, then the force from this spring is actually directed to the right. So here, this will be k times y in the I direction. Likewise, if you look at, say, Fs2, if z is positive, then this force acting on the block will be directed up. Right? So Fs2 here is k times z in the j direction. So this is kz in the j direction. And then likewise, this is minus kz in the j direction. So that these two forces are of equal magnitude, opposite direction. Finally, the reaction force, it's just unknown. Right? So I'll write that as Rx in the I direction plus Ry in the j direction. So now we have a description of the forces. We have the kinematics from the previous slide, and we're ready to apply the equations of motion. Right. So let's apply angular momentum balance on the disk. Right, so that's basically the sum of the moments, and we'll take moments about O, the center of the disk, or the mass center. Notice that doing this eliminates the reaction force. The reaction force produces no moment about the center simply because it acts at the center. So we need to calculate the moments acting about O. I'll remind you of how we calculate moments. Right, so imagine you have an object here, and you have a force here, F, that's acting at, say, a point P, and I have a second point, A, here, and I'd like to find the moment about A. It's the position of P with respect to A. Right, so we call that RP with respect to A, cross the force itself. Right, so again, when we calculate moments, we use the cross product, R position of the application of the force with respect to the point that we're taking the moment about. So it's R cross F. So now if I look at these forces acting on the disk, this force acts at this point, right? So straight above point O. Right? So as a result, we can calculate the moment as minus k times y R over 2 in the k direction. Now looking at this force, it acts over to the left, so working through the cross product, we would get plus k times z in the r direction, or sorry, k times z times r, the radius, in the k direction. And that's going to be the moment of inertia, which in this case is mr squared over 2 times the angular acceleration, theta double dot k. Right, so I-O alpha of the disk. Right, so again, the general laws of mechanics are I alpha equals sum of the moments. So here we have our equation for the disk. And now, on the block, we'll apply linear momentum balance. Right, so that's going to be some of the forces here on the block. Well, there's just one force. We've neglected gravity. So we have kz in the j direction equals the mass times acceleration. So that's minus mx double dot in the j direction. And remember we did the kinematics here, and the acceleration of the block was minus x double dot. So that's the mass of the block times the acceleration of the block. So again, that's going to be sum of the forces equals mass times acceleration. So now, from this, we can pull off two equations. One of them looks like minus k r over 2 y plus k times r times z equals mr squared over 2 theta double dot. And the second equation looks like k times z equals minus mx double dot. So notice that I have two equations, right? But I have 5 unknowns. Well, actually I only have 4 unknowns here. I've got y, z, theta, and x. So I can now use my constraint equations. Let's go back and remember what those were. Here, y, w, and x, to fill out this set. Right? So y is equal to r over 2 times theta, x, or sorry, w is equal to r times theta, and finally x is equal to w plus z. All right, so just to kind of highlight where those coordinates fit in, there was y, z, we boxed in green, theta we had gray, orange for x, oh there's another theta, and then finally our fifth equation, or our fifth coordinate, we'll do is w. So now we have 1, 2, 3, 4, 5 equations and 5 unknowns. So I can choose any two coordinates, any two independent coordinates that I want. Here we said that we wanted to write this in terms of theta and x. Right? So in particular, we need to eliminate y, w, and z. Well, y and w are directly in terms of theta. Notice that here z is equal to x minus w, which is equal to x minus r theta. So taking these relationships, using them in the momentum balance equations, we get the following. mr squared over 2, so I'll take angular momentum balance first, and I'll write everything here in terms of theta and x. So we'll bring these two to the other side, so it's plus k r over 2 times y, which is r over 2 times theta, minus k times r times z, which is x minus r theta, equals 0. And mx double dot, using linear momentum balance, plus k times z, which was x minus r theta, equals 0. So I can actually clean this up a little bit and combine some terms. So the final equations of motion are mr squared over 2 plus 5kr squared over 4. Notice that I have a kr squared over 4 here, and then I've got another kr squared there, minus kr times x equals 0. And the second equation is mx double dot minus kr theta plus kx equals 0. Right, so ultimately, these are the equations of motion. Right, we have two equations in terms of x and theta. And I just realized that I am missing, I didn't write the theta double dot here. So we'll go ahead and put that in. So again, here are the equations of motion. But let's do a little more. Right, we're not done yet. So here I have rewritten the equations of motion, and I would like to actually take these and put them in matrix form. So I want to identify, for example, mass matrix, stiffness matrix, that sort of thing. So now in matrix form, right, we can write this as mr squared over 2 times theta double dot. Notice that there's no x double dot piece, so we have a 0 in that element. Now the stiffness matrix looks like 5k r squared over 4. And again, theta and x. And then for the x term, we have minus k times r equals 0. The second equation, there's no theta double dot term, so we get a 0 there. There's an mx double dot term. So we have mx double dot, and then notice that this is minus k times r times theta, and then plus k times x equals 0. So here, this is the mass matrix. M. And then likewise, this is the stiffness matrix. Which we define as K. Very similar to what we would have with a single degree of freedom system. Mass times acceleration plus stiffness times displacement equals 0. Now, I do want to point out that if we were to choose different coordinates, we would get a different result. So, for example, let's choose W and Z. This is about the most unusual set of coordinates I could think of for this problem. So we're going to describe the motion of this system now in terms of this displacement of the upper point of the spring, and then Z, the stretch across the spring. Notice that that's fine because W is related to theta. Z and W are definitely related to X. So we can do this. And when we look at this transformation, we see that, well, again, y is equal to W over 2. Theta would be solved as W divided by R, and X would be W plus Z. And the resulting equations could be written as mr over 2 W double dot plus kr over 4 times W minus krz equals 0. And I've sort of done this offline. You might want to go through and actually see if you can get these results as well. The second equation becomes mw double dot plus mz double dot plus k times z equals 0. So with this, we would find the system would look like mr over 2, 0, m, and then m. This would be our mass matrix, and our vector of coordinates is w and z. Our stiffness matrix would be kr over 4, and then minus kr. Here we have no w term, so we get a 0 there. We just have k in that element. and then of course this is equal to 0. So once again, we're able to identify a mass matrix M and a stiffness matrix K. But notice that these two stiffness matrices look completely different, as do the mass matrices. Completely different. So the system that you get depends on the coordinates that you choose, which kind of makes sense, right? If you're measuring different things, you might expect that you would get different equations. However, there are some fundamental things about the mass and the stiffness matrix in both cases that are the same, and we'll look at that when we start talking about how to actually solve these problems. Right, so here it is. This is another example deriving multi-degree of freedom systems. Thanks a lot, and I will talk to you again.